All right, we can get started. Okay. It's already 3:10, so I'll leave the door open. Okay. All right, so today's Wednesday, of course. Let's see. It's probably a good idea to get started on the homework if you haven't already. So we're going to set up some office hours, I guess, for Jacob now that we've got a key for him, so he can be in, the office of room 379. But we don't know exactly when, so we're thinking Thursday sometime. Okay, so I don't know if there's you can send us emails if you have an idea of a time that's good for you. If you haven't been able to come to office hours on Monday, Wednesday, Friday, and maybe, especially if you can't show up to the help sessions on Friday, then that'd be a good time for you. Okay. So we'll do that. And we will have a help session this Friday evening, probably in the ARC building, as always. Okay, so you should get started on PA5 though. And so from my discussions so far with students, probably the hardest part, the trickiest part to wrap your head around in PA5 is going to be the new part, which is this desugaring path. Okay, so before we had a parser and an interpreter. Well, now there's something that sits in between. That's the desugarer. Okay, that gets rid of the syntactic sugar and kind of sort of compiles them down into more primitive features of the language. Okay, but the key thing to realize there is that that's before the interpreter. That you're not actually interpreting or evaluating anything in the desugaring phase. All right, and you're just performing a syntactic transformation. You're taking one piece of syntax and transforming it into an equivalent one that implements the behavior of the original, so that when you do evaluate that, it will give you the same result as if you had evaluated the original. And given that the interpreter knew about the original syntax, but the point is that it doesn't know about. So for example, we're doing this with Boolean conjunction and disjunction. Okay, so in the source language, we have expressions that look kind of like, and E1, E2, and or E1, E2. Okay, and the idea is that these should be short-circuiting logical operators. Okay, just like in C++ or whatever, where in C++ you can do something similar, like E1, I think it's double ampersand E2. Okay, and this is a logical conjunction of two Booleans, but it has a special behavior called short-circuiting, where if E1 is true, if E1 is false, then you can short-circuit because the whole expression will be false, and so you actually don't have to evaluate E2 at all. Okay, but for disjunction, it's the other way around, where if E1 is true, you go ahead and short circuit, because that the disjunction will be true already, right? So that's what we're doing here. That's the intended semantics of these expressions, but we're not going to actually extend our interpreter to know about them at all, because we already have, the interpreter can already do conditional expressions, which are sufficient for implementing these. Okay? So the idea is that your desugarer should be able to look at an expression. So I'll say D for desugar. I should be able to look at one of these expressions and just translate it into another expression that is equivalent and that implements the short-circuiting behavior. Okay? And we're not doing any evaluation yet. You're not going to run it. Okay? You can't actually like check the values of E1 and E2. These are just kind of like black box expressions. You don't know what they are. Okay? And you're just going to arrange for things such that whenever the interpreter does run the expression, it will do the right thing. It will implement the intended semantics of these. Okay. So that's what you have to do for the assignment. Okay. Okay. And the other thing about this assignment is that we're adding functions. That's kind of the big thing. So I'd like to remind you. Okay. And so I'm going to review this big step semantics thing. Let's go scheme 1 score big step. Okay. So I'd like to remind you of this document and hope that you are not too afraid when you look at it, because it can be very helpful for you when you're, especially when you get around to functions and you're wondering, how in the world do I implement the interpreter for functions? And the answer is right here if you can figure out how to read this. Okay. So for example, in the eFun case, right, this tells you how to evaluate a function expression. It looks like this: fun x e, e is the body, and it's actually really quite straightforward. There's sort of nothing to do. Okay, you just turn it into a closure, and you're saving the environment in the closure, right? And then for function application, that's where the real magic happens. Where you've got an application expression that looks like this, where there's just some E1 on the left side and some E2 on the right, and you've got your environment that you're evaluating under, and then this tells you how to evaluate the application. And in short, it's evaluate E1 to a closure, and evaluate E2 to some value, and then use that value for the argument in the environment. So when you evaluate the body of the function under a modified environment here, where you're binding the formal parameter of the function x to the value for the argument. Okay, and take note that this is row prime here, which was the row inside of the closure, not the ambience environment that you're evaluating under. Okay. Right, and so if you remember, this is called the big step semantics, because it's written as a relation between expressions and values. It's always like that. Okay, all these things are like, well, you've got an environment, and then an expression, and a value. And this relation states that under the environment row, this expression evaluates to this value. All, in one big step. Okay, so we're not really taking account of every little step of evaluation and how it goes on, but it's all in one big step. It's a little bit coarse-grained. That's why it's called big step semantics. Big step operational semantics, to be clear. Okay, so I want to write this down. Okay, where it's one instance of operational semantics, and it's the big step kind. Okay. So what I might do, I don't know. We might actually have to look at small step semantics as well whenever we get to the type safety theorem, because I realize that big step semantics are actually not quite sufficient for stating type safety. So that could be interesting for us to kind of try to do it and see what goes wrong. And then we can take a look at small step semantics, where small step semantics is kind of the same thing, except it's more fine-grained. And so there's going to be more rules, and it kind of tells you more exactly how to carry out evaluation one step at a time. Okay, and so then it'll actually tell you like the order of evaluation. So it'll tell you here, you definitely have to evaluate like the left side first for a binary expression, for example. And then once that's a value, then you evaluate E2 one step at a time until it's a value, and then you can continue. So hopefully we'll get to that. Okay. Right. And I know we're supposed to be talking about types, but there's still, the type system's kind of intertwined with the runtime semantics. The whole point of the type system is to kind of predict runtime behavior in a way to rule out bad cases. So we can't really get away from talking about this stuff even when we're talking about types. And I was thinking that maybe, I don't know, because I mentioned another type of semantics. So remember, this is operational semantics. But there's another kind that I mentioned called denotational semantics that is also interesting. Okay. Denotational semantics, which is a little bit more abstract usually. It's sort of more like mathematical in nature, where you're saying, well, we're going to provide a denotation function. And so for us, it'll be on expressions. Our programs are just expressions. So we'll have some like denotation function. You can use this, okay, where the argument goes in the dot. It'll be an expression there. So this whole thing, takes x and maps it to whatever we want. The idea is that you're going to interpret expressions as something, okay, into some kind of mathematical domain, some sort of mathematical objects, okay? So you're asking, well, what's the interpretation of a given expression? Okay, so it's just kind of a different perspective, a different way of going about it, okay? And so for us, as I mentioned, what you might do at first is to say, well, what does an expression denote? It's a value, right? So we should be able to do this. We should be able to come up with a denotational mapping that maps expressions to values, where the interpretation of a given expression is just some value. Okay, but of course that doesn't work because expressions can contain free variables. So what about if this is what we were doing? What if you tried to do this? Plus x1. Okay, there's an expression here, and we want to interpret that expression as a value. And you say, well, we don't know how to do that because there's this variable x here. Okay, so really, what we do, instead of saying that an expression denotes a value, we say an expression denotes a function from environments to values. Okay, so that's how we're interpreting expressions, is as functions from environments to values. Okay, so then what would the denotation of this one be? Plus x1. Well, it would be a function. Okay, I'll write as a lambda that takes an environment, which I'll call rho. Okay, and then it'll look up x in rho and add 1 to it. Okay, which we can write, rho of x plus 1. All right. So this function is our interpretation of this expression. Okay. So it's kind of a neat way to go about it. Okay. So we could have actually written our interpreter more explicitly in that way. So if you look at the type of our interpreter, what does it do? Well, it takes an environment and an expression and gives you a resultant val. Well, we could kind of refactor this to correspond more closely to this denotational semantics that we might want to define, where what it does is it takes just an expression and gives you the interpretation of that expression as a function from an environment to resultant val. Okay. And so now this is one way of setting up this function, where it's just, what's the interpretation of an expression? as a function from environments to results. And we can step through a couple cases here just to see what it looks like. Let's see, what were all the X constructors? Here they are. I'll just copy them down. There's one for val, right? What do you do when the expression is a single value? It's like, well, the value, you just want to return that value, right? It doesn't care about the environment. And so, well, it's just the function, a lambda that ignores the argument and gives you OK of v, right? It's the constant function at v. There might even be, there's not, but sometimes you can define a helper for that sort of thing. Okay, but what about ident? Identifier where x is some string. Then what do? It's like, well, here's one thing. You could take, you take row, and then just look it up. Look up row x. Okay, and then similarly for the others. So for Unix, well, we can do Unix a little bit maybe. E1. Okay, so now if you look, when you interpret E1 recursively, instead of giving you a result of val, it gives you one of these, a function from environment of val to result of val. So you have to go ahead and really do something like, you have to pass it on. Okay, and then there will be something, you'll do like cases on U maybe. Okay, but that's not super important. But we could have written our interpreter this way. And there's some little tricks you can do, like, for example, this is kind of unsatisfying in a way. And it made me realize that I probably wrote lookup kind of in the wrong way. Okay, it's unfortunate that lookup takes its environment argument first. So what if our lookup function, instead of taking row and x at the same time, actually just takes x first. Okay, and so we're writing it in curried form where it takes one argument at a time. Okay, and so now it has to be changed a little bit to be like this. So if we had written our lookup function in that way, then we can do something a lot cleaner here. Instead of having a lambda, you can just say lookup of x. Just apply lookup to x. Okay, we're using partial application here. So here's an example. There were some questions in the past about like, when is this sort of thing useful? When are curried functions useful in partial application? And here's one example where it really cleans up this code. Because you think, what is lookup of x? Well, it's just our lookup specialized to the string to lookup, and now it's a function from environment to result of val, which is exactly what we needed here. Okay, so that's our interpretation of an identifier expression. Is the function that it looks up x in the environment. Okay. So I don't know. I just thought maybe that was a good example of using partial application. Okay, that if we wanted to write our interpreter in this way. Okay. But that's all I want to say about denotational semantics. That's a very deep rabbit hole that you can go down with denotational semantics, and there's a whole field of mathematics really called domain theory. There's pretty much about denotational semantics of programming languages. That's where it came from, and it was all started by a man named Dana Scott in like 1969 or 1970, and he's quite old now, but he's still alive, and he's very, very well known. So kind of a legend of computer science. Okay, especially in programming languages. Anyway, how much time do we have? Quite a bit. So now I suppose we can get to types and type systems. Okay? And we can look at sort of how you might add a type system to the Scheme 0 language that we had. So, we're looking at PA4 here. This is the language without functions. Okay, and so there's a way to do this. It's very similar to what we did here with the big step semantics. Okay, where here, what did we define here? The relation between expressions and values. Okay, where there's this relation that we were doing. We said, well, E down arrow V with row turnstile to say E steps to V, or E evaluates to V in one big step. Well, we can do a similar thing called the typing relation. Okay, that will now be a relation between E, expressions E, and a type T. And I'll write it like this. So you pronounce this, E has type T. Okay, and of course it looks very similar to the pirate syntax for, where it's a double colon. Okay, well, I'll just use a single colon here. Okay, so we're going to define a relation like this by giving us a collection of inference rules for determining when it's true. Right? When is it the case that a given expression has a given type T? Okay, and just like before, where you had a row environment for variables that could appear free in E, well, we're going to have a similar thing for variables that appear free in E, called the typing context. Okay, that instead of mapping variables to values, we'll map variables to their types. Okay, so that whenever you're type checking an expression, you need to know the types of the variables that appear free inside of it. Okay, so we'll use a capital gamma for that. So that's just our notation for the typing context, and it's essentially the same thing as the variable environment, except instead of mapping variables to values, it maps them to their types. Okay? Yeah. And I just remembered, I have some slides that we could look at about types, just a handful of slides. So I don't know if that's a good idea. Perhaps I'll wait until Friday. Maybe we'll just go on for now. Okay. Okay, so, well, we want to define this typing relation. Okay? This is how we'll define the type system. I mean, so really there are two parts to a type system. One is, what are the types? You have a language of types. So for us, what are our types? Well, we'll have bool. I'll call it tbool, and we'll have tnum. Okay, so we have Boolean and number types. And I think for this language in PA4, that's probably all that we need, because those are the only kinds of values that we have, Booleans and numbers. There are no functions yet. Okay, we don't have product types or anything like that. There's really just these two base types, and that's it. Okay? Okay, so that's step one, is to establish what the types are. Of course, you could have more than just the base types. Say we wanted to add product types to the language, well then you could have like, T times T as another kind of type, okay, like a compound type. But for now we don't have that. Okay. So now we really just need to consider all the possibilities for the syntax of E. And what were they? Well, one of them is a value. Okay, so let's write a typing rule for values. Okay, so you've got some value V. And really, we'll have two. I suppose we could treat them separately. We'll have to have two different rules. There's one for numbers and there's one for Booleans. Okay, so suppose you've got a number value. Okay, and it can have type tnum. And when is that the case? Well, it's always the case. Okay, so we don't have to put anything above the line here. There's nothing else to show. This is like an axiom of the type system, that any number value just has type num. All right, so you can always conclude that for free. Okay, and I'll give a name to this rule. Call it t_num. Okay, and then there will be a similar one for Boolean. Suppose you've got some Boolean value. And you could, I could write separate rules for true and false if I wanted, I suppose. But I'll just let B stand for either true or false. And we'll say that that has type t bool. Again, always. There are no obligations above the line. There's nothing else to show. You can always conclude that a Boolean value has type t bool. So these are the axioms, you could say, of the type system. Okay. Oh, and I forgot to include the context. Right? It's always under some context. Big gamma. And like this little thing is called the turnstile. It doesn't really matter, but that's what you usually use. Okay. All right. So what's the next kind? Now that we've handled all the possible values, well, there's identifiers. Okay. And I'll use X to denote an identifier. And I'll say, well, X has type T when, well, if you remember, there's this. We have this context. So when does a variable have type T under a given typing context? It's when the typing context has a binding for X, mapping it to T. And so the notation, we could use this notation that we used before. So like if gamma is a function that maps variables to their types, then this would be what we need. So you can conclude that a variable X has type T under context gamma whenever gamma maps X to that type T. Okay, but sometimes what people will do is they think of gamma here as actually a collection of pairs, like a collection of bindings. So like an example of gamma could be like maybe there's a binding for X mapping it to T, and suppose there's like a binding for Y mapping it to some other. Okay, so it's like a list of bindings. And so sometimes in this in the typing relation, this will be written slightly differently, which is just that this binding is in gamma. Okay, so I think that's what I did in the document that we'll look at later. Okay, but it means the same thing. All right, so I'll call this T var. That's the typing rule for variables or for identifiers, and it's pretty similar to the evaluation rule for identifiers. It's like, well, you just look them up in the environment or in the context. This third page after. Now we get to some more interesting ones. We've got unary expressions. And of course, there's only one kind of unary expression. And that was, I believe, not. So you've got an expression that looks like not E. And, well, our intention here for not is that it should only work for Booleans. Okay? That was the idea. That when you run the interpreter on not E, it'll run an error, or it'll throw an error if E is not a Boolean. Okay? So our type system should be enforcing that. It should say, well, in order for not E to have a type, in order for it to be well typed, then E should have type Boolean. Okay? And the whole thing in that case will have type Boolean. Okay? So this is going to say bool. Okay? But not E will have type bool under what conditions? Well, can't forget the context. But, well, whenever E has type T bool under the same context. So we'll call this T not. Okay, so here's our typing rule for unary negation of Booleans. That you can conclude that an expression that looks like this has type T bool, provided that you can show that E has type T bool. So here's our first kind of recursive rule, right? That when you're implementing the type checker, to implement this, what does this mean? It means kind of recursively checking E, right? And then checking that it has type bool, then the whole thing will have type bool. All right? Now we have bin exps. So I suppose there are two situations here for binary expressions, because here are the possible bin ops. And so the first four of them, add, sub, mul, and div, well, they take number arguments and produce number results, right? But then the next two, EQU and LT, that's equality and less than comparison, they take two numbers as arguments still, but they produce booleans for their output. Okay, so they're going to be a little bit different. There are kind of two cases here for binary expressions. Okay, so let's do one of them. And I'm going to use B to stand for a binary expression. Maybe it's not smart to overload this B variable because I used it to stand for booleans earlier. But that's okay. And so we're in gamma. And so I'll do the first case where this will be tnum. Okay? And what do we want here? When are we able to conclude that some bin op applied to E1 and E2 has type tnum? It's like, well, this should be one of those bin ops that has a tnum return type. So I'll go ahead and say, well, this should be plus, minus, times, or division. Okay, so that's one thing to check. And then really it's pretty straightforward. We just need both of the operands to have type tnum, right? So I'll go ahead and write that. E1 has type tnum, and E2 has type tnum, all under the same typing context. I'll call this T, I don't know, arith, binop, or something. Okay, so there's one of the rules for binary expressions. For whenever the bin op is one of these. So we'll need another rule. Yeah? Oh, yeah.
So are we not allowing checking the lengths on inputs? I mean, I know it would be redundant because it seems to be inactive, but are we not allowing comparing booleans using the equal?
Right, we're not. So it should only work for numbers. That's just not. That's
I know that's not out there yet.
right. Yeah, so that is going to be an important point here, is that the typing relation is like this. It's the smallest relation. Formally, we'll take the typing relation to be the smallest relation that's closed under all of these inference rules. And what that really means is that once we've written out the rules, that's it. And that those are the only rules that apply. Those are the only way for an expression to be well typed, and there's no other way. And so if you're ever in a situation where one of the rules doesn't apply, well then, your expression type pair is not in the relation, so that expression is not well typed. And so, yeah, we are going to arrange the type system so that whenever we have like equality and less than, which will be the next thing we do, if the operands have type bool, then there's not going to be a rule that applies. Okay, we're only going to have a rule where E1 has to have type tnum and E2 has type tnum, and that's it. And that's a choice that we're making. I'm trying to think.
Is that something that would be worth handling in the future?
You could do that. Yeah, you could do that, but it would be kind of hard because it's hard in the desugarer so the desugarer is going to run before the type checker. Now, you can interleave them. It's actually not a rare thing to do, to kind of desugaring and type checking at the same time. But if we're keeping them separate and you're desugaring before type checking, that means you don't have type information yet when you're running the desugarer. And so then whenever you see an equality operation, you don't know if it's on numbers or booleans yet, in general. But you could do that if you mixed it with the type checker. That is possible. Right, but yeah, so we're not going to support equality checking on Booleans or less than on Booleans. And that's just because, well, I don't know if I have a good answer other than just we're keeping the type system simple, okay? And that generally there's only one type for a given operator, right? That it's not overloaded for different types, because our type system is very simple. Okay. So let me write the next rule. For the others, okay, and this will be the tbool. So the whole thing will be Boolean whenever b is equals or less than, and again E1 has type tnum and E2 has type tnum. Okay. Right.
Shouldn't this be tbool? Or okay.
No, it should be tnum. Right, because we can only compare numbers. And I feel like I'm blanking. I feel like there's a better reason for why this is to answer your question, but I'm not sure how to answer that because what if we added another rule? Oops. For this, and I forgot my thing. E1, E2. That is kind of the same, but had them be, or really we could replace both rules by just using a variable t here to assert that they're the same. Whatever they are, they should be the same, and so they could be number or Boolean. But here I'll write this out the way that I started. I'm trying to think of what goes wrong here when you have both of these rules, because I'm not sure that it is, although there might be something kind of undesirable about it, which is that the relation is no longer syntax directed. That's a weird word, where generally what we want is you want to be able to look at the syntax of the expression in the goal under the line and be able to tell just from looking at that which rule to apply. And if we have these, that's no longer true. And so when the relation is not syntax directed, in general it can be more difficult to translate it into an algorithm for checking. Okay? And so there is a distinction when you're writing these type system things like this, that sometimes they're not algorithmic, okay, or they're not syntax directed. It's just a declarative type system. And then you have to translate it into a similar version that actually is syntax directed, so that it can be turned into an algorithm on a computer. Okay, but ours is sufficiently simple that it is syntax directed. It translates very directly to an algorithm on a computer. And you could, I think, maybe we could do this technically. But you have to do a little bit more than just looking at the syntax of the expression. That you'd have to kind of try type checking it as a number or a Boolean and do some extra branching there. So it may be possible here in this case, but I know in general it's better to try to keep it syntax directed so that you know what rule to apply just from looking at this. Okay. And well, maybe that's it. I mean, perhaps there's some other moral arguments for why it's just good design to not do that, but I'm not sure at the moment. Okay. Got a few minutes left. So we've done binx, and we've done we've done binx. This is exhaustive now. Okay. So ITE is next. So let's do ITE. Okay, so we're under gamma, and we've got an ITE expression. I'll just write it if E1, E2, E3. Okay? Okay, so here's where there's actually something kind of interesting to do, because, you know, I mean, this has come up before earlier in the class where we were interpreting, or when you were like parsing if expressions and you were wondering, like, should we care if this is a Boolean or not? But of course, the parser doesn't care. The parser just cares that it's an expression there, right? And the parser is perfectly happy with anything as long as it parses as an expression. Okay, but then once you get to the type checker, now is when you're interested in checking for that. Okay, so what I'll say is that a conditional expression like this will have type T under a few conditions here. And the first is the obvious one. The E1 should have type T bool. Right? So here's where we check for that. Okay, and then the other two, what we're going to say is that we don't care what their type is as long as they're the same. Okay, and well, they should be T. Okay, so as long as E1 and E3, or E2 and E3 both have type T under gamma, then the whole thing will have type T no matter what, because then, you know, regardless of which branch you take, you'll get a T in either one. So the whole thing will be T eventually. When you run it, it'll give you a value of type T. So E2 should have type T, and E3 should have type T. I can give a name for this: T bool bin op T cond. Okay, so there's the typing rule for conditionals. And then there's one more that we have time for, which is the let expressions. We have let x be E1 and E2. So let's write that. We've got let x be E1 and E2 under the typing context gamma. And we'll say this has some type T. Well, I might have to use, I'll call it T2 here. Under what conditions? Okay, so this one's interesting as well. What we'll do is say, well, let's type check E1 under gamma. Okay, so you should be able to type check E1 to get some type T1. Okay, so E1 should be well typed with some type T1. Okay, and then when we type check E2, we have to take that into account somehow. Okay, that we want to type check E2 not under gamma here, but under an extended context where there's a new binding mapping x to the type of E1, which we've called T1. Okay, so this is just like when you were, interpreting a let expression. You first interpret E1, and then kind of, continue interpreting E2 under an extended environment where now you've bound x to the value from E1. Well, since the type checker is just kind of predicting what will happen there, and we want to be able to check if E2 can run safely and have a type, then you just need to make sure that it's well typed whenever there's a type for x in it. So here's what we'll do. We'll take gamma and extend it with a new binding, mapping x to T1. And that's the environment, or that's the context under which E2 should have type T2. Okay? And if that's the case, then this whole thing is well typed and has type T2. So it's called T-let. Okay? And now we've covered everything. Okay? And so here's actually a fully defined typing relation for a little type system for scheme 0 core, the language from PA4. And I'm not going to prove this, but I believe we could prove the type safety theorem here, which says that if you've got an expression and it has a type according to this relation, then when you run it, it'll run to a value. You won't get an error. Okay, and maybe we're out of time now, but maybe next time I can at least state that theorem to show you what it would look like. Okay, but what that means, that's sort of like it means that this type system is good. It's good enough that it rules out all the bad programs. Okay, that's what we're going for. Okay, so now we're out of time, so we might have a quiz, right? Wow. All right. See you Friday. Jeez.